So, good afternoon, everybody. So this lecture, I will talk mainly about constraints in inverse dynamics and forward dynamics. But first, let me, as I promised, these are comments. It's a new feature of PowerPoint I discovered. Let me talk to you about something that we didn't have time to talk last time in the lecture on Newton-Euler Equation, actually. So we arrived to define the floating-based dynamics, the dynamics for a floating-based robot, seeing that a different parameterization of the central mass of the generalized velocity using the velocity of the central mass was leading to a decoupled equation, one underactuated and one actuated. And the underactuated one was corresponding to the Newton-Euler equations. So in particular, now we can detail the Newton-Euler equation and see how are they written and how there are smarter way to write them in a way to speed up, for example, optimizations. Newton-Euler equation describes the motion of a rigid body, so we are no longer talking here about an articulated robot, but a single rigid body, where the force and moments are applied at the central mass. And they represent the conservation of the linear and angular momentum. In particular, the Newton equation, as you know, it can be seen as the variation, links the variation of the linear momentum to the external forces applied to the body. And you can write this way, defining actually the linear momentum as the mass times the velocity of the central mass, and it will have the well-known form of acceleration times mass, total mass of the body, equal to the sum of the forces applied and the gravity, which is also an external force. The contact forces, for example, this can be the external forces, can be the contact forces, and we see from this equation that to move in a direction different from gravity, we need to have some contact forces. Otherwise, the gravity will dictate the direction of the acceleration. But this equation is linear. From knowing f, I can integrate and obtain the central mass trajectory evolution of the central mass. Because and very simple, the dynamic is linear. But if you look at the Euler equation, it's the angular equivalent of the Newton equation and relates the variation of the angular momentum about a point, because when you talk about angular momentum, you always need to define a point respect to what you want to compute it. We call this pivot point. I say this point is the central mass. The variation of angular momentum about the central mass is equal to the action, the sum of external moments about that point. So if you have some forces, like here we compute the moment doing the cross product with the point of application, and we can find the external momentum due to the action of these forces is equal to kg dot. So if in this case, you see you need to the lever arm between the rotation of the force and the central mass is xf minus xum cross fy, you get external moments. But how does this term kg dot look like? First, let me do a quick detour on how do we compute the derivative of a point in a rotating frame. In a rotating frame, for example, if we have a vector that is moving, that represents the location of a point in a rotating frame, we have two components in the derivative. One is the explicit time dependence due to the motion of this point in the rotating frame, and the other component is due to the motion due to the frame rotation, to the rotation of the frame itself, and is related, as you know, to the change of direction. Because even if you have a constant vector in a rotating frame, the direction, even if the magnitude is the same, the direction will change. And so to account for this, let's say we are defining the position of this point in an inertial frame W, and we have that the point P is its a position relative. It is the position of the frame G plus the relative position in the frame G rotated in the inertial frame. And if you differentiate this, we get that we have the velocity of the frame G plus we have the rotation matrix times the derivative of this relative vector plus the derivative of the rotation matrix times the derivative vector. And we saw last time, or remember a while ago, that you can define the derivative of rotation matrix this way, where omega is the angular velocity of the frame G with respect to expressing the frame W, so this is wrong. And you therefore you can this is simply the relative velocity of the point P in the frame G expressed in W, and this is the linear velocity of the frame G, so this is the relative, what we say, the change of magnitude, and this is the variation which is expressed as omega cross x GP, which is the variation due to the change of the rotating frame. If these two frames are just rotating, one is rotating but the other, but the relative distance is not changing, this term is 0. Okay. So now we can, putting this to aside in your mind, we can try to define the Euler equation in an inertial frame. So let's say we have G equal to the inertia, tensor of inertia of the rigid body times P omega. Now let's say we have the derivative of Lg times the derivative of omega plus the derivative about time of Lg times omega. Now, depending in which frame you write the equation, first of all, this is true for any reference frame. We know that Lg is constant if we consider the rigid body and we express, for example, the inertia at the center of mass. So if we express, first you need to think about this is the inertia expressed at the center of mass point, and you should also define which frame you want to define it. So if you define it in a frame that moves with the body, then Lg is constant. If you define a frame that is, for example, aligned with the inertial one, then it's time variant. And this is the third possibility. This is a situation where the inertia changes with time. Here the frame is Lg here is computed about this point. Here is computed about central mass, but in a frame that is aligned with W, so it's still changing with time. While in the case of a frame moving with the body, the inertia is constant. Clear? Okay. So let's say now we want to express this Euler equation in a frame that it's attached to the center of mass, but it's aligned with the inertial one, which is mostly the case in robotics. I will call this frame W bar to distinguish from W, which instead is outside the body and attached to the floor of the lab. So this frame W moves with the body, but it's always aligned with gravity. It's alignment is inertial. So in this case, we have from CAD, we normally from our CAD software where we model our robot in 3D, we can compute the value of the tensor of inertia in the central mass frame, aligned with the body, let's say with the frame of the body, and to compute the tensor of inertia in the frame W, we need to pre and post multiply by the rotation matrix that maps the frame G into W. And this means that since the rotation matrix is time varying with the orientation of the body, then the derivative of this with tensor of inertia with respect to time will not be zero. It will not be constant. The tensor of inertia is no longer constant. So yeah, to simplify the notation, we just call this matrix R. So if we want to compute now the Euler equation, which is, we said, is the derivative of kg equal to external moment, then we can replace the LW with this. This is LW omega. We get R and G, and this is constant. I transpose W. Now, if we distribute the differentiation over there, we can get the first term times the second differentiated, and dot, plus the derivative of the second term. So in this case we have R, L, R transpose. So first we differentiate R, L, R transpose. Then the second term is constant, so we don't differentiate it, and the third term is we give this as this, and we differentiate this. And this is times omega. Now we said that R could be seen as omega cross R, but you can also see the transpose equivalent as R transpose cross omega. And if you swap the term and you put a minus, you get minus R transpose, sorry, omega transpose, where if you swap the systematic matrix associated to the cross product. Then we can place here, and you can see that here we still get again LW, and here we get in essence omega cross R LG R transpose, and this is again LW, plus another term that is R G, sorry, R LG, the minus R transpose omega cross, everything multiplied by omega. Now if we write this, up, we can obtain LW omega dot, right? This term here, and then we get two terms. The first one is omega cross LW omega plus, I would say minus, this is again LW minus LW omega cross omega. Now this is cross product of two of the same vector itself, it's 0, so it's, you can eliminate and we get the expression of the Euler equation in an inertial frame attached to the central mass. So this term, it's due to the derivative, let's say, of in a rotating frame, and we need to pay attention that this omega, this inertia changes with time. These are the main point of this formulation. Now, while we have this term, we in the Newton equation we don't have it because the mass is invariant with the reference frame, but the extra term here is due to the fact that the inertia changes with the reference frame. In general, ideally, we could even have that this term it's 0 in specific situation wherever the vector omega and I cross omega are aligned. But in general, this is not the case. And this term here is the one that makes such that if you, for example, you drop a pen from the top, this pen ideally the momentum should conserve, but it will start to rotate because it's not that these two guys are not perfectly aligned. So in general, LW is not aligned with W. They are aligned only whenever you have, for example, the tensor of inertia is perfectly diagonal. But let's see. We said that we have this inertia that is changing with time. This means that if we use it in an optimization, and we are writing symbolic equation, blah blah blah, it will take a lot of time to deal with that, because we're going to have rotation matrix in there, which is the cosine and sine, so there are some nonlinearity there. If we would like to use, for example, the constant inertia expressed as a central mass, for example, but we could even express it in another point of the body, like the base frame or whatever other point is constant, such that it doesn't change. And we can see what we should do to formulate this equation in a rotating frame. So this time we need to replace, we start from the previous formulation, no? Where we have the LW omega W, and we replace we compute the angular velocity expressed in the rotating frame. So now we are thinking about the inertial frame here and a frame rotating with the body attached to the central mass. So this frame is rotating. And with the rotation matrix, we can map the angular velocity in the G frame into the work frame. And the same for the moments. So here it's missing one part. Yeah. Then This time we can compute the angular momentum in the G frame and just rotate it. And if we differentiate, again we get the first term times the derivative of the second. This time L is constant, so we only differentiate the omega, plus we have the derivative of R times the second term. Okay. Now we can prove that this is true, but also if we express R dot is also equal to if you express the omega in the rotating frame, it's the two-term swap, and we have this expression. So we can replace this R dot with R dw omega cross. And here we get GW, the moment bulk. Now if you left multiply all the equation for RGW transpose, we have that this term modified, we have LGW plus GW transpose. This also goes away, and we have mg cross mg omega g. So, and here also this goes. So we have, in essence, a very similar structure, but this time, well, we still have this term because the frame is rotating, and we will have a similar one if we express the Newton equation in a rotating frame. But the problem of this approach is that all the vectors are expressed in the rotating frame. So before doing everything, we need to compute the angular velocity in the central in the G frame and also the external moment in the G frame. But I believe this is not a big problem in general. It's just a rotation matrix, and it improves a lot the speed of the optimization, as our student here knows. Miraj implemented it and found quite a lot of improvement. The conservation of the angular momentum also if we write the equation in a frame that is not central at the central mass. Until now, we always talk about frames attached at the central mass, either aligning with the inertial frame or moving with the body. But we could do, you could express in a frame outside the body, which is fixed. In this case, you will have a relative distance, change in velocity and distance between the rotating frame and the frame you express the equation. And this creates a lot of problem because a lot of Coriolis, centrifugal, acceleration, a lot of fictitious acceleration comes out, which is very complex to deal with Euclidean algebra. I spent quite some hours today trying to derivate it, but in the end I ran out of time. But the ideal approach in this case is to use spatial algebra, which as the equation it's always the same with disregarding of the reference frame wherever you write it. And so if you are interested to do that, I can talk more about this offline. And the last part, I want to just point you out, this is an optional part just to let you think, is that it's a non-holonomy of the angular momentum dynamics. So if we are not talking anymore about a rigid body, but we talk about a robot, an articulated body, so a set of links attached, we have that, yes, the conservation of momentum still holds, but we have that our inertia is time varying, not only because if you express in an inertial frame it will change, but also because of the motion of the joints. Because if you know, if the dancer stays with the hand like this, the inertia increases, the dancer starts like this, then it rotates faster, and maybe it's just, there are no external forces, it's only pivoting about one point, and it will speed up faster. Why? Because this term changes, so it will create a change in the omega rate. So we have this internal movement of the joints that affects the angular momentum rate, that we call gesticulation. And this is exactly the strategy that a cat uses whenever he's falling and he wants to reorient himself to land straight. So I don't know if you ever tried to do this experiment. Take your cat. It's not very nice for him, but it's very educative. You tip it, so you put with the back pointing down, and then you let it fall, and it will reorient himself with the tail. Using the tail, it will change the inertia in a way that will create will reorient in the space. So when we talk about ergonomic constraints, we say that a constraint on velocity, it's a constraint on position. It can be computed one-to-one from integrating a constraint from velocity. So, for example, the contact constraint is a non-holonomy constraint, because if you say the contact for velocity is 0, then if you integrate, the position of the contact is constant. But in the case of, for example, of the conservation of angular momentum, we say that this product should be constant. So we have a constraint on the angular velocity. And it's said to be non-holonomic because, as we said, the orientation is not obtained simply integrating omega, but we can change the orientation also controlling the joint of the system. So we cannot straightforwardly compute the orientation from omega because of this coupling, dynamic coupling, and this is exactly the strategy that a falling cat uses to reorient itself. So moving the joints can influence the orientation due to the non-holonomic coupling between the rotation of the system and the joint configuration. Okay. Everything is clear now? This was just an interesting point of view, especially if you read the paper of Weber about non-holonomy or non-holonomy. It's talking extensively about this. Go to the next topic, which is Constraint Dynamics. So first we talk about the constraint forward dynamics, and then we talk about the constraint inverse dynamics. The constraint forward dynamics is useful, for example, whenever you want to build a simulator, you want to simulate your system, and you have contacts, and you want to deal with contacts. And actually there is a smart way to remove, so you know that whenever you are in contact, then your torque affects the contact forces, and the contact forces are also affecting acceleration, and so everything is quite coupled. And there is a smart way to deal with that. So let's think about the fluid dynamics, which is given certain set of torque. We want to compute the acceleration of the system whenever it is in contact, even if it is in contact. So the first part is the usual equation. This time we are talking about a floating base robot. So we have the selection matrix for the torque, and this acceleration are n plus 6 belongs to the manifold of n plus 6 of dimension n plus 6, and the contact forces are satisfying the constraint of the contact at the acceleration level. And this is, of course, we are using here the rigid contact assumption. We will see afterwards with the soft contact how does it work. So in here we need to get both acceleration and contact forces, and it's a smart way is to try to eliminate the contact forces from the equation. So to do that, first we solve for q dot dot, and we can insert it into the second equation. So yeah, let's say we first we compute q dot dot. We have the contact forces, and then we replace in j q dot dot plus j dot q dot equal to 0. We get j m minus 1 s transpose tau sh plus j transpose f plus j dot q dot. Now we solve for the contact forces. So we get the contact forces j transpose times f plus j m minus 1 times s transpose tau minus h plus j dot. And we can compute the contact forces. We already did that a while ago. We see that here we have the joint inertia reflected at the end effector, at the contact, sorry. And we can plug it back. We can plug it back in the dynamics. So if we put the contact forces there, plus h equal to s transpose tau plus j transpose. This goes to the right, so f it's j m minus 1 j transpose minus 1. This we call it lambda, which is the rotation space inertia. And we have this on the other side, so minus j dot q dot minus j minus 1 s transpose tau times h. Okay. Yeah. If you keep developing this product, you can find this term. We don't care, but there is another term which is very interesting, which is this one. So we see that h appears as an identity, and here appears multiplied by this term. And also s tau appears with an identity and appears also multiplied by this term. So what this term looks like? Let's remember you remember the Euler inverse of J transpose, how does it look like? So J transpose, it's a skinny matrix, right? So the Euler inverse of J transpose, it should be a fat matrix. Which is equal to J transpose, the transpose of the matrix itself, times J transpose times the matrix minus 1 times the transpose of the matrix itself. And this is J transpose minus 1 J. But we're still not there. There is a weighting matrix here that in the Euler inverse, so we are not talking about a Euler inverse, but a weighted Euler inverse, where the matrix W is the inverse of the inertial matrix. So if we put the weighting matrix in the middle, and as weighting matrix we use the inverse of the inertial matrix, we get this term here, okay? So now if we collect, and we call this term the dynamically consistent Euler inverse of JT, where we weight with the inertial matrix. Now if we collect this term and this term and this term and this term, sorry, yes, so this term and this term and this term and this, we see that we are getting something like this, which really reminds me of the new space projector for the forces that we compute in the lecture on operational space.
Does it work if the J matrix is a fat matrix instead of a skinny matrix because of the degrees of freedom of the robot?
Yeah, normally, yeah, the task is smaller than the number of degrees of freedom of the robot, so yeah, but it could be the other way around.
It could be
in
the
that
other way.
case, you need to do the proper computation of the inverse. But yes, most of the time, the Jacobian is fat, is said to be fat, or at maximum square.
Okay.
In the case, for example, of a quadruped, you have the square Jacobian whenever you have all the feet on the ground, the four legs. But in the other cases, it's rectangular fat. So, so let's say we collect the term from the previous equation, and we get something I minus J transpose Euler inverse times H, sorry, it should be on the right side, plus the term we don't care, which is this one. I think that there was a minus there. Yes. It was on the other side, so we put on this side there is a plus now. Equal to I minus J transpose Euler inverse ST top. So that if we, you remember when we map from the torque, the space of the torques, that is n-dimensional to the space of the end effector, let's say that is lower dimensional than this, you can get, you can have a new space, and you map there with the J transpose Euler inverse. So whenever you have a vector tau, and you multiply for j transpose cell inverse, you filter out whatever is in the null space, and you get here, and then when you go back, you get in the row space. So this is a row space projector, and in the null space projector, it's the orthogonal complement. So this is, in essence, is a null space projector of the J transpose matrix. Sorry, the J transpose pseudo-inverse matrix. And this represents the torques, tau and S, that do not produce any contact force, but only joint accelerations. So they can move the joint internally, if you've ever done this especially, but they don't produce any force of the contact. Note that the computation of n requires that J is full rank, and also the weighted version, we are talking about the weighted version here, is non-symmetric. So there are some people that are not considering this, but it's in the weighted version of the cell inverse, the space projector is non-symmetric. Then we can write this dynamics. That is the dynamics written in a space that is contact consistent. So imagine that you have n plus 6 dynamics, and and this dynamics is the projection of the full dynamics in a reduced manifold wherever the constraints are satisfied. And not only that, but most important, this is NH plus n most important, we will see that the contact force has disappeared from the equation. So if you we will see this afterwards. There is a way to simplify this, replacing, for example, this term, ugly term, j dot q dot, with minus j q dot, and we see that we can simplify more this equation, and we get the null space projector outside this term times this. So it's like multiplying left and right hand side for the null space projector. It's like projecting all this equation in this compact consistent subspace. And as I said, the contact force disappeared from the equation because we said we have F forces. We go back to the row space with J transpose, so we get some torques. And if these torques, so these are torques that are in the row space, we multiply for the null space projector, the two are orthogonal, so the result will be 0. So this is actually starting from the beginning. You multiply this part for n. You multiply st transpose tau for n, and you pre-multiply n times j transpose f, and this goes to 0, so you remain with that. This is to close the loop. So, and it's, as I said, a linear operator that maps the dynamics into a constraint manifold, such that the equation of motion is independent of the contact forces. And we could select any operator that satisfies this. So it's up to you. There are many papers about computational advantages of using one operator rather than another one, but I won't go into these details. So now that we are fine, we can compute our accelerations, right? To do the simulation. But we cannot do that because this matrix is not invertible, because nm is singular because n, because of n. For this reason, we have some methods to deal with that, to write in another way. This paper, if you're interested to, but for now we use the previous formulation, that this one that we wrote here, and we will implement this in the lab of today.
Can you use the pseudo inverse for the matrix that is not square?
Yeah, you can do it, but you introduce some inaccuracies. And let's say we are using for now the four-dollar integration of the root approach to compute from the acceleration the velocity and the positions. And this will be contact consistent. But yeah, this is a detail. This term it's almost zero for non-redundant manipulators, because they are in a non-redundant manipulator. The task dictates the motion of the joint, so you don't have anything in the null space. No motion in the null space, but there is one problem. Whenever the robot gets in contact, what happens? The robot is starting to get close to the blackboard and then touch the blackboard. What's going on?
Some kind of force depending on the insertion into the area surface.
Let's say we are using a rigid contact function, and a contact force will appear.
Velocity goes to zero.
Yeah. So the velocity drops instantaneously to zero if we model the contact as inelastic. This means that there is like some impulse that decelerates instantaneously the contact point velocity to zero. Okay. So because we have an inelastic impact. But how do we compute? Whenever the effective velocity goes to zero, we also have that the joint velocities should change instantaneously to be consistent with this condition. Before was different than zero, now is equal to zero. So there should be a change in the velocity, in the vector of velocity, between before the impact and after impact. Okay, and to compute that, at the touchdown, you see we have velocity equal to zero, force appears, collision not landing, foot point immediately go to rest. And to compute it, we need to integrate the dynamics through the impact. If we check the Ergonomic dynamics and we integrate through the impact before and after the impact, we see that all non-impulsive forces drop out, so we can see like the action of an impulse and the variation of linear momentum in the joint space, and all the non-impulsive forces drop out, and we can consider that after collision, the foot of the contact point is zero, and this is equal to j q dot plus after the impact. And we can compute that from there, that q dot plus minus q dot minus times mass is equal to j transpose this impulse. And if we can relate j q plus to the q dot plus to the q dot before the impact with this n minus 1 j transpose we have the blue one. Now if we replace this into here, we can get x f dot equal to j q dot minus plus m minus 1 j dot j transpose fc. And knowing that this is 0, we can compute finally the impulse fc, which serves us also only to relate the variables, and we compute it as minus j minus 1 j transpose j q dot minus. And you see that again and again we have the inertial matrix and the contact popping out. Now to compute the post-impact velocity, we replace Fc into here, and we can compute q dot plus equal to q dot minus plus m minus 1 j transpose j m minus 1 j transpose minus 1 j q dot with a minus. Now let's collect the q dot minus, and again we get m minus 1 j transpose j m minus 1 j transpose j. And what is this?
Constraint Dynamics.
Of what? The space projector of what?
Of the contact point.
No, of the matrix J. So this is working at the velocity level this time. So you see, we have this time we have J pseudo inverse weighted with M. Okay, but this is J pseudo inverse J, and this is we saw in the lecture on the inverse kinematics. For Dante manipulator is to map velocities to project velocities in a space that doesn't affect the end effector velocity. So all these velocities that we multiply here will result in velocities that don't produce any effect on the end effector, which is exactly what we were looking for, because we wanted that the end effector velocity is 0 at the contact. So only at the moment of contact, whenever you detect the contact, you update your velocity vector multiplying by the null space projector of J, and that's it. Okay, and you start using the constraint inverse dynamics, and this you will see in the lab. And of course, this n is this null space projector is different from the previous one because this is acting at the velocity level and not at the top level. Just a quick note on energy loss in collisions. You can relate the energy loss as the kinetic energy that you lose to get in contact, and you can relate the joint space variable to task space variables this way. And if you replace, you can compute the kinetic energy loss as this way, which is the operational space equivalent of the joint space kinetic energy with the spatial the effective inertia, contact inertia, rather than the joint space inertia. This is an interesting thing. I mean, this is completely optional. It will not be part of the exam, I think. But it's interesting to know. It's the Gauss principle of least constraint that tells let's make an example of a set of particles with mass under reaction of some forces, and you have some constraints between the motion of these particles, and these are the unconstrained particles with the same forces, same set of forces, and the acceleration of the system of particles deviates from the unconstrained accelerations in a least square sense. This is what the Gauss principle says. So in essence, you solve a QP. The constraint acceleration are the ones that are obtained solving a QP, wherever you try to minimize the norm, quadratic norm weighted with the inertia matrix from distance from the unconstrained acceleration, subject to the contact constraints. So we compute the unconstrained acceleration in the case of our robot as the usual dynamic equation without any constraint. You plug this in, you solve the QP adding these contact constraints, and the q dot constraint that you obtain should be consistent with the q dot that we computed with the projected constraint inverse dynamics, constraint dynamics. And you can verify this in the lab. It's done, and you can verify this is true. Of course, in the case of the QP, you need to split this way. You have like this is your decision variable. There's a transpose missing here. This is your known term. So if you develop this, you get q dot. First you do this, plus you have the term minus q unconstrained transpose q dot. Then you have the other term q dot transpose and q dot bc, plus you have the so this is a minus. You have the last one, which is q c dot transpose. This is not part of our, it's not a decision variable, so it doesn't affect, we cannot, it doesn't help in the minimization of our costs, so we can remove it, and we can write it, and then, so here it was 1/2. We can see that this is a scalar, okay? This is a quadratic form, you get a scalar, but you also get a scalar from here. So in a scalar, the transpose is equal to itself. So if we transpose this, we can sum these two terms because they are the same, and we get this expression minus the sum of these two becomes 1, q dot transpose UC and q dot. So whenever you will call your QP problem, you put this matrix in, and this G, this is the linear curve. And yeah. And that's it. Now, we discussed about the rigid contact assumption, but there are many simulators. I think Gazebo is one of these that use a soft contact model. And in this case, we already talked about it previously. We model the contact as a spring damper, for example, and the force will obey a specific equation that links the evolution to the penetration between the bodies. In this case, for example, the factor of the foot of your robot and the floor, for example, and then you can put it there and solve for the acceleration. Then compute the acceleration, you compute the motion of the body, and then you can again take the force and iterate. You can express different spring and dampers different directions. So you can have a 3D spring, for example, and you can define even generic law for the force, for example, on a linear spring. And this is what it's going on. You have a contact model that computes this force getting to the rigid body dynamics. You have the controller that provides the torque given the tracking error, and then rigid body dynamics with torque and forces. You can compute this time forces. It will be not an unknown because it will be provided by the contact model, and then you can compute the acceleration and such the integration, the velocity, and the positions of the joints, and then with the contact model you can compute again the value of the force. So to summarize some advantages and disadvantages of the contact model, two contact models, the compliant soft contact models are easy to compute. However, it is difficult to tune the parameter of the contact. In particular, most of the time you need stiff springs because you want to model a rigid ground, for example. And this means that in that loop here, you get an algebraic equation that makes your ODE become stiff, numerically stiff. Numerically stiff means that you need to reduce the integration step around the contact, and that's slow simulations. While the rigid contact is straightforward to integrate, and is preferred whenever you do, for example, some analysis rather than the simulation, because it can become pathological, for example, when you use it for optimization, if you need to differentiate it. Let's say this is the a graph wherever you have the contact force and the penetration is there. So this is zero penetration, and you say you know that the rigid model has the famous complementarity condition, where the complementarity condition says that you can this product times f should be zero. This means that if you have positive, if you are not in contact, your force will be zero. Whenever you get in contact, your contact will be remain the same. There will be no penetration. You can have force. So you can have only force in contact, and this is very pathological because it's non-convex in optimization. Instead, a soft model tells you, for example, if you have a spring, that because from penetration you get some times k, you get some force. So you can get here. So you move around this, and if you have a soft spring, you have like this, and you see that as long as k increases, the soft model approaches the rigid model.
Why do you use the rigid for stability analysis?
But yeah, for example, because you can drop for example, from the equation you can drop the contact forces. You can do. It's easier to do a stability analysis on the acceleration zone.
I don't need to differentiate there. So in all the cases when I don't need to.
I mean, think about you want to do a Lyapunov stability analysis, and you want to don't have the contact forces inside. You just want the dynamic equation, and in that case, it's easier with the constraint dynamics. Yeah. I will. If you have any, do you have any question about this?
So the least square solution of the QP that you said is equivalent to the pseudo-inverse solution that you get. That's what you were saying, because the weighting matrix in there is a mass which is fixed, so you can use that and just find, because also the pseudo-inverse is the least square solution of the linear system.
For an unconstrained QP, the pseudo-inverse is equivalent, but this is a constrained QP in the case of the Gauss principle, so it's not equivalent. Absolutely, you have a constraint, the contact constraint added on top.
So how does the solution become equivalent for both of them? Let's say if I were to take only the pseudo-inverse and then solve the same problem with the QP, with this formulation, we have the same solution. You say
I would need to think if it's possible to come from the probably it's equivalent because you enforce the contact constraint as it's a Lagrange multiplier, and then you solve the QP, and probably you will have the same equation in the QP solution of the QP as in the case of the pseudo-inverse.
Yeah, because that would actually solve a problem of having let's say pseudo-inverse in the formulation. Let's say if we were to consider in the optimization and directly take the least square formulation in the optimization. Let's say if you have bi-level optimization, you could actually have two objective functions interacting with each other, where one is doing something at the planar level and another one where you have to find the solution for this QP solution. So to find the inverse, let's say inverse of the pseudo matrix using only optimization than doing let's say pseudo inverse itself separately.
Yeah, this is just an alternative, but nobody does it. I think because it's just time consuming. Like just computing the constraint inverse dynamic was just cool to show that it's equivalent. Nothing. It's not practical use, I would say. Okay. So what time is now? I will do a quick break of. Let's say 5-10 minutes, or you want me to go with the inverse dynamics part and then we do the lab?
Break.
Okay.